In this lesson, we're going to look at choosing a system for analysis and deciding whether it is isolated, determining the force behind a change in momentum, and using bar charts and tables for data organization. You've previously studied momentum and impulse. They're both extensions of dynamics. Momentum and velocity both describe motion. Momentum, in fact, is mass times velocity. Momentum, like velocity, is a vector, so it has direction as well as magnitude. Impulse describes a change in momentum produced by a force acting over a period of time. You know that forces cause changes in velocity. Forces also cause changes in momentum. Impulse and force are both vectors, so they have direction as well as magnitude. I have this block set up so that one side of this specially made ball will knock it over. Just to demonstrate the two sides of the ball, side A is not bouncy, not elastic, whereas side B is bouncy, elastic. So my question to you is, which side will knock over the block? Please take a moment and record your answer. So right now we've got side A. Okay, I'm going to turn the apparatus around so that we can strike the block with side B. All right, side B. Let's analyze this demonstration both graphically and mathematically so that we can determine which side of the ball transfers the most momentum to the block. I like to use an organizing table for my variables and a momentum bar chart to see what's happening. Let's look at side A, the non-bouncy side, first. So as you can see, we've got a chart set up. I've identified our system as the ball because we have a very complicated arrangement. We've got the ball, the string, the block, the table. Friction is present between the block and the table. So we're going to just choose the ball, and our system is not going to be isolated because the block, which is external to the system, interacts with the ball. We're going to take right as positive, and I've already drawn pictures for before and after and filled in the variables. Our before picture takes place immediately before the ball strikes the block. The ball is moving horizontally to the right with a velocity v initial. We have an initial momentum of mv initial. The after picture takes place immediately after the ball strikes the block. Side A does not bounce. We have no velocity after the collision. This gives us a final momentum of 0. Now we'll fill in the momentum bar chart. Since we don't have numbers, I'll just shade in 2 blocks for the initial momentum. I'll darken the 0 line for the final momentum. Clearly the momentum has changed, and we need to represent that change on the chart. Following along with the calculation, we've got impulse is equal to a change in momentum. Since the mass is constant, I can express this as mass times change in velocity, or mass times velocity final minus velocity initial. Substituting our values from up above, we have mass times 0 minus velocity initial, which gives us an impulse of negative mass times initial velocity. So let's fill in the bar chart to record this change in momentum. In other words, the change in momentum, or impulse, is the same magnitude but opposite in direction to the initial momentum. So it takes an impulse of negative the initial momentum to bring the momentum of the ball to 0. Remember that the impulse bar only gets filled in if an external force acts on the system. In this case, the block, which was external to our system, exerted enough force on the ball to stop it. Now let's look at side B, the bouncy side. I've got the system, the coordinates, axis, and the sketch already filled in. We have the same initial momentum, but this time the velocity immediately following the collision is negative what the initial velocity was. So our final momentum is negative mass times initial velocity. Again, I'll shade in 2 blocks to represent our initial momentum. But this time, our final momentum will be negative 2 blocks. Same as the initial momentum, but in the opposite direction. Let's look at the impulse equation again. So we still have mass times final velocity minus initial velocity. This time, substituting my values, I've got my final velocity is negative my initial velocity minus my initial velocity. So that gives me minus 2 times mass times initial velocity. So in other words, we've got double the initial momentum, only it's negative this time. So I've shaded in 4 blocks below the 0 line to indicate our change in momentum. It took the same amount of momentum as ball A to bring the momentum of the ball to 0, and again that much to bring the ball to negative the initial momentum. So for our bar chart, I'll need to fill in 4 blocks below the 0 line to represent the total impulse of negative 2 times the initial momentum. According to Newton's third law, the force applied by the block to the ball is the same as the force applied by the ball to the block. Newton's third also holds for momentum. The momentum transferred by the ball to the block is the same as the momentum transferred by the block to the ball. Impulse can also be calculated as average force times an interval of time. We can assume the collisions for both sides of the ball took the same amount of time. The more momentum transferred in the same amount of time means the greater average force applied to the block. The greater the force, the more likely the block is to tip over. Which side caused the block to tip over? Side B, the bouncy side. Which side applied the greatest average force to the block? Again, side B. Which side experienced the greatest change in momentum? Once again, side B. Which side transferred the most momentum? You guessed it, side B. So we see that side B transfers more momentum to the block than side A. Now you'll use these ideas in the activities to follow.